So we talked about reaction rates and how we can measure average and instantaneous reaction rates and how that's all very nice and good, but it doesn't tell us anything about what's going to happen in the future. And so that's where rate laws are much more useful. These show the relationship between the reaction rate and the concentration of the reactants. So for an extremely simple reaction where we have A making some products, this is the rate law. The rate of the reaction is equal to K times the concentration of A raised to the n power. So K is called the rate constant, N is called the reaction order. Now the reaction order can be lots of different numbers, but the most common are 0, 1, and 2. So those are the ones we're going to talk about. In a zero order reaction, the rate is independent of the concentration. Doesn't matter how much there is. Rate stays the same. First order, the rate is directly proportional. Second order, the rate is proportional to the square of the concentration. Other orders are possible, even fractional orders like half or 3 halves. Yeah. So here we have a graph of concentration versus time. This is the sort of thing we looked at on Tuesday. So here for this blue one, we see that as time goes on, the concentration goes down. And that's true for all of these. But we can notice that how it goes down is different, right? For a zero order, it's a straight line. For first and second order, it's a curve. If we look at rate versus reactant concentration, the rate versus the concentration, for a zero order reaction, we see that the rate doesn't change with concentration. It's just equal to the rate constant because A to the 0 power is 1. So there's no concentration in the rate law. Doesn't matter, it just is what it is. First order, we have a direct proportionality, and so we see a straight line here. Second order, it's proportional to the square, and so this is an exponential curve. Any questions? Zero order reactions are kind of special. They're not super common because you think, well, how could the rate not depend on the concentration of the stuff? Well, it can happen when solids are reacting. So here we have a solid substance that's subliming. It's going directly into the gas state and then condensing on this test tube. When one layer of this leaves, there's still the same amount left to react, right, available to sublime. So as you peel off a layer, there's still the same number of stuff, right? So in essence, the concentration isn't changing. And so that's why it doesn't depend on the concentration. The amount of reactant available for reaction isn't changed. Okay, it's kind of weird. First order, the rate is directly proportional. So here we've written the 1 just to sort of emphasize it, but normally we wouldn't write an exponent of 1, right? So here we see that the rate slows down as the reaction goes on because the reactant concentration is decreasing. Second order, we have A to the squared. Remember, A with brackets around it is the concentration of A in moles per liter. So the rate is equal to some constant times A squared. Here the rate's even more sensitive to concentration. Okay, let's see if we understood that. Again, looking at a very simple reaction, A going to products. It says doubling the concentration of A causes the reaction rate to double. What is the order of the reaction? 0, first, or second? First order, yeah. So we're doubling A, and then the rate doubles. Now, for some people, they hear double twice, and they think 2. Understandable. This is not second order. This is first order. It's directly proportional. So this is the answer. If we look at, come on, the rate is equal to K times A. So when this is to the first power, it's just A. So if we multiply this by 2, the rate gets multiplied by 2. If we multiply this by 4, the rate gets multiplied by 4. If this was a second order reaction, and we multiplied this by 2, this would get multiplied by 2 squared, or 4, right? And if this was 0, A to the 0 is 1. You can do whatever you want to the concentration. It's not going to change the rate. Okay, any questions?
So you can read that, it says products, a doubling of the concentration of A causes the reaction rate to double. You can just kind of read that and say, well, one is proportional to the other, so it has to be first,
Yes,
right? Okay.
exactly. That's exactly right. So you're looking at the relationship between those two. Are they doing the same thing? It's first order. Is the rate doing the square of what the reaction concentration is? That's second order. Does changing the reaction not, changing the concentration not do anything to the rate? Then it's 0 order. Yeah. How do we determine the reaction order? The order of a reaction can be determined only by experiment. We'll learn something a little bit later that you'll really like and you'll want to do it all the time, but you can't. I'm not going to tell you about it now because then you'll start doing it now. The order of reaction can only be determined by experiment. You cannot look at the equation and say, oh, that's second order for this or first order for that. You can't. You just can't. So how do we figure it out? One way is called the method of initial rates. So you measure the initial rate of the reaction starting with different concentrations, and you see what happens. So here what they did is they started with 0.1 molar A, 0.2 molar A, and 0.4 molar A. They measured the rates. So from this data, we can tell what order it is. What we want to do is we want to look at how did this change? It doubled. How did the rate change? It doubled. So this is first order. If you multiply the concentration by a factor, you multiply the rate by the same factor. So it says determine the reaction order. So we determined it was first. And so then we can write the rate law. The rate is equal to rate constant times the concentration of A. Bless you. Now it says determine the rate constant. The rate constant is K. We need this equation, the rate law, in order to do this. Over here, we have 3 sets of data. We have the rate and the concentration that go together, right? And in this equation, there's 3 variables, the rate constant, and the concentration. If we know 2, we can find the third. So let's look at the first one. So the first one, 0.015 is the rate as units of molarity per second. That's equal to the rate constant times the concentration of A. So we're going to solve that for K. Oops, I already did that. Just dividing by 0.1. I'm not going to do all the algebra the whole semester, so. Try that again. So it's 0.15. And we talked about, no, we didn't, never mind. That was the other class. What happens to the units over here? We've got molarity per second divided by molarity. It's tempting to say seconds.
Molarity squared.
No? Inverse seconds. Yeah, so it's 1 over seconds. Or s to the minus 1. So we have a fraction divided by something. So dividing by m is the same as multiplying by 1 over m. And now we can see the m's are canceling out. Any questions? Yeah.
So the rate constant isn't 0.15 over s, it's 0.15 over inverse, right?
Well, it's 0.15 divided by seconds, or 0.15 times inverse seconds. It's confusing, huh? You familiar with hertz? A frequency measurement? Hertz is cycles per second, right? How many times does this thing happen per second? Except the cycle part isn't included in the units. So something's revolving, it's this many revolutions per second. If it's bouncing, it's this many bounces per second, but it's just expressed as per second. It's not necessarily going to make very much sense.
So in
It's
this case, the rate constant is 0.15
per second.
per second.
Mhm. Yeah.
That's all.
Any other questions? What do we do if the reaction order is not obvious? Well, actually, let me talk about these two examples first. So here we see that there was a doubling of the concentration, and what happened to the rate?
Stayed constant.
Stayed the same, nothing happened. We double it again, nothing happens. 0 order. Here, double the concentration, quadruple, right? And if that doesn't pop out to you as times 4, take 60 divided by 15 is 4. And again, times 2 here is times 4 there, because 4 is 2 squared.
Sorry, I was just noticing something.
Okay. So sometimes we have some nice data and we can figure it out, especially if the orders are nice. But what if the orders are like fractions or something?
I'm gonna cry.
Ew is right. Yeah. So then we can use this equation here. And that looks complicated. What it is you take the rate law under one set of conditions and you divide it by the rate law under a different set of conditions. So 2 and 1, so we could call this number 1 and that one number 2. And so then we would take the rates, take this one divided by that one. That's going to equal the rate constant times this to a power divided by the rate constant times that to a power. Does the rate constant change? No, it's constant. It's in the name. So the rate constants cancel out. So I'll work out an example with that in a future slide. Let's look at the units for rate constants. You could memorize these. For me, it's just easier to figure them out. I don't need them that often, and I'm going to show you how you can just figure it out. It's actually fairly quick. So here we have the zero order rate law. What are the units of rate? Molarity per second. We don't know what the units of K are. A is in molarity, but it's raised to the 0 power, so it's just 1. So the rate constant has units of molarity per second. So let's look at this one. Again, the rate is molarity per second. We don't know what the rate constant is. And now the concentration is in molarity. Depending on how you view things like this, divide by m on both sides or cancel the m's out, you're left with 1 over second. S to the minus 1. Second order. So if you know the units and you just see a rate constant, if it's 0, 1, or 2, you can actually just pick it out because of the units on the rate constant. It's not super useful, but it's handy once in a while. The reaction A to B has been determined to be second order. The initial rate is 0.01 at an initial concentration of 0.1. What's the initial rate when A is 0.5? So A is changing from 0.1 to 0.5. What are we doing? Multiplying by 5, right? 0.5 divided by 0.1 is 5. So initially it was 0.1, and now it's 0.5. So it's being multiplied by 5. This is a second order reaction, so what do we multiply the rate by? 5 to the second power. 5 squared. So the initial rate was oops. I bet you didn't know that was a number. Oops. Or maybe it's a landmark on the coast of somewhere. So if we take 0.0100 molarity per second and multiply by 5 squared, so this is a conceptual question. So, I want to do that in my head, but I'm like, it's so easy to mess up where the decimal is, right? Well, let's look at the choices. 5 squared is 25. So which one of these does it have to be? It has to be D. That's the only one that you'd get from multiplying 1 by 25. Yeah. Where did the square come from? Great question. The square came from it being second order.
So if it says second order, it's squared.
Yep.
And then first order is just the third power.
Right. Yep. In 0 order, you don't do anything. They say, oh, we quadrupled the concentration. Rate stays the same. How do you know? It was 0 order. If you quadruple the concentration in its first order, you quadruple the rate. You multiply the rate by the same number. Multiply 1 by 4, you multiply the other by 4. If it's second order and I multiply the first one by 4, I multiply the second one, the rate, by 4 squared, or 16. Any questions? What if we have more than one reactant? We're going to consider the generic equation. It's the alphabet reaction. AAs plus BBs, etc. So A is the coefficient, the lowercase a is the coefficient, capital A is the formula. So we can write a rate law from the equation, but we don't know what the orders are. We're going to have variables in there. So what we did before with 1 is we had a variable that was n. Well, now we've got a second reactant, and so that other one's going to have an exponent of m. I don't care what you call them. You can call them x and y if you want, or give them cute little names. It doesn't matter. I don't know why they didn't put the n here and the m there. I don't know. Well, I guess because it's alphabetical. But we were using n before. I don't know. Is what it is. So we can write this generic rate law, but we don't know what the orders are because the rate law for any reaction must always be determined by experiment. So we can look at m is the order with respect to A, n is the order with respect to B. If we want to know what the overall order is, we add those together. So give the overall order and the order with respect to each reactant. So here's a chemical reaction, here's the rate law. So what's the overall order? 2. Overall order is 1 plus 1, which is 2. How about the order with respect to hydrogen? 1. And with respect to iodine? 1. So it's the exponent here. Again, we wrote the ones when we usually don't, just to kind of be obvious. And so, just to watch out, there are some things in this class that seem too simple, right? It couldn't be that easy. Well, yeah, we put those in there just to mess you up. No, we didn't. But yeah, it's just that simple. Whatever the exponent is, that's the order for that reactant. The overall reactant order, add them together. Okay, so let's look at the second example. What's the overall order? 3. 1 plus 2 equals 3. So for hydrogen, what's the order? 1. And for, no! 2. It would have been fun if you got it wrong, and I could have said no real loud again. It's all caps, it's yelling. Right? No! I have 6 kids, that's one of my favorite words. No!
Don't do that.
And now that, most of the kids have moved out of the house, now we have 4 dogs. So I probably say no more than I did before. Anyway, do you see how that works? Yes? That's an excellent question. Why is this first order? Because somebody did an experiment and figured out that it was.
So,
You want it to be 2, don't you?
yeah.
Yeah. Has nothing to do with the coefficients.
Okay.
Awesome.
Yeah. Yes,
Is that always the case?
it's always the case.
It has nothing to do with coefficients.
Coincidentally, they could be the same, right? Here, the orders happen to be the same as the coefficient. Is that always true? Absolutely not. Here, the no was second order, and it had a coefficient of 2. Are those two things related to each other? No, it's coincidence. Utter coincidence. And this is one of the problems because it would be so nice if it was just the coefficient, right? But it isn't. It isn't. Any other questions? Consider this chemical equation. Measured the initial rate of reaction at several different concentrations. Got these results. From the data, determine the rate law and the rate constant. Well, we can rough out the rate law. CHCl3 raised to some power times the concentration of the second reactant raised to some other power. That's the closest we can get. Now what we need to do is we need to look at our data, and if they did the experiment properly, we'll be able to figure it out from the data. So here we have the first reactant changing, and the second reactant is not changing. So in going from 1 to 2 here, that doesn't change, so it doesn't matter what that order is, it's not going to affect anything because it didn't change. That makes sense? So any change in the rate here is because of this change, okay? So here we doubled the concentration. And then over here, it's really close to double. 0.0069 divided by 0.0035, 1.97. Some people are very happy to round that to 2. Other people are like, that's not 2. This is real data. It has error in it. Any data has error because you measure something. Anytime you measure something, there's error. It's horrible, but you can't get around it, so you just have to get over it. So the fact that it isn't perfect doesn't worry me at all, okay? So that is essentially times 2. So double the concentration, double the rate, what's the order? First order. So we can erase the M, and we could just leave it blank, or we could put a 1 in there. Everybody okay with that? You could also look at, well, no, you couldn't. Never mind. So to find the order for the other one, we need to find a pair of experiments where the Cl2 changes and this doesn't change. So what's that going to be? This one. So any change in the rate is because of the change in the Cl2 concentration. How does this change? 0098 divided by 0069. Very unsatisfying number.
Yeah.
No one should be comfortable with rounding that to 1. It's not even close. The order doesn't have to be a whole number. It could be a fraction. But if it's a fraction, we're not going to be able to see what the fraction is here. And that's why we need to do that rate law divided by the other rate law. So, well, let's be consistent. Rate 2 over rate 1 is equal to the constant times CHCl3 to the first power times Cl2 to the n power. So this is 2 and 2, and down here we're looking at concentration 1. Kind of looks like a mess, doesn't it?
Yeah.
Yeah. What I'm doing, though, is I'm taking this guy, which hopefully that's not too messy for you. I'm taking this for this second set of conditions, the second line, and that's on top. And then I'm going to take this again with a different set of numbers and divide by that. If the rate equals this, and the rate equals that, then I can divide them by each other and it's still true. So rate 2 was well, I'm talking about doing these two, but I don't need to do that. What I want to do is these two, right? Let's just highlight those guys. We want to compare this one and this one. We could do it with the first one, but we already figured that one out, so it's kind of a waste of time. Okay, so 0098. And the rate in the first example there is 0.0069. Does the rate constant change? No, that cancels out. Now, we could put in the concentration for the other reactant, but it's the same, right? It's canceling out. Let's go ahead and put it in there anyway. 0.020 and 0.020. Those are going to cancel out. And then we have the Cl2 concentration. So Cl2 concentration in the second row is 0.02 to the n power. And in the first one, it was 0.01 to the n power. Now, you might think, how is this helping? We have an equation now with one variable. We can solve for the n. It involves a little bit of logarithm stuff. So if we do the math there, we already did 0.098 divided by 0.069, that was 1.42. That's equal to 0.02 over 0.01, which is 2 to the n power. And then if I take the log of both sides, taking the log of something brings the exponent down. And what did I do wrong there? Is 2 the exponent? No. And when I went to solve that, I'm like, wait a minute. The exponent, okay, I'm willing to bet money that this business didn't make sense to at least a couple of people in this room. So I'm going to show you how you can do this without doing logarithms. Cool. Okay, so we've got this guy right here. 0.0098 divided by 0.0069, and that is equal to 0.0, let's never know, 0.02 to the n power divided by 0.01 to the n power. And we got that by taking this, kind of messy thing here, but we just plugged the numbers in. We didn't actually do any math. Now, if you don't like algebra and you want to see magic tricks, be sure to grab one of these calculators if you don't own one yourself, because I'm going to show you how you can get this calculator to take that and tell you 0.5. It's super cool. You see that? If I don't stand in front of it, you can. So on this calculator, there's this blue number solver. So the blue things go with the button underneath. So I press second to get the number solver. If it's been used before, it's going to have whatever got left. I'm going to hit clear to get a little box, and I'm going to move the cursor to the right and hit clear. If it's never been used, it's going to show you box equals box. I need to type this equation in just as it looks. We could do that. So I have a fraction on the left side, so it's a really good idea to use this little fraction button, because now you don't have to worry about two denominators multiplied and that you're screwing it up or anything like that. Just like it looks. So on the top, I'm going to point 0098, on the bottom, point 0069. You could put the zeros before the decimal points. It's going to work either way. I'm going to go over here, and I'm going to press that button again because I have another fraction. And now I'm going to have 0.02, and I want to raise that to the power of n. So this guy right here will raise whatever you've got there to a power that you tell it. So it's waiting for me to give the exponent. On here it's an n. Well, the calculator will do a bunch of letters. It doesn't do n. Could we use x instead? Sure we could. This is our variable button. Look what it does. X, Y, Z, T, A, B, C, and then back to, D, and then back to X. I just always use X because it's the first one. So 0.02 to the X power, and then I'm going to come down here, and I've got 0.01 to the X power. That's just copying, right? I'm going to press enter.
The screen got
Little
blurry.
bit, and
Screen got fuzzy. Okay.
There we go.
Is that better? Okay, I don't know what I did, but I'm glad I fixed it. I'll try not to touch anything. X equals, and it's just got the number that was the answer to the last time that this was used. You could start with that. I think it's safer to just always start with 0. So I'm just going to type 0. It's going to solve this problem by iteration, meaning it's going to start with whatever I give it, and that's not going to be right. And so then it's going to try something else, and try something else, and try something else, and get closer and closer and closer. Sometimes it takes a little while, like 15 seconds, which seems like forever, but it'll get there. So I press enter here, I press enter here, and I wait.
This is really fun.
Oh, that was only like 10 seconds. What does it say? 0.506. It's the same number I got. Was that easier? Now, people who like algebra, they're like, yeah, I don't know. But we're going to do some stuff where the alternative to using that is to solve the quadratic equation. I love algebra. I don't want to do the quadratic equation. That's just a mess. So this will do the quadratic equation for us, and it's just really great. And, there's the math in this class is a little more advanced than in Chem 1A. We're not actually doing any calculus, but the algebra, there's more exponents and logarithms and things like that to watch out for. So even when you're not doing a quadratic, you just got kind of messy equation and you need to solve for one of the variables. Instead of having to rearrange everything and possibly make mistakes, type it in the way it looks, and it'll tell you what the answer is. I think that's pretty cool. Now this took me a while to figure out. So if I get out of that, and I'm like, but I need to use that number for something now. I didn't write it down. Where is it? It's X.
Oh,
I know, right?
joy.
I'm glad I didn't keep track of how many years it took me to figure that out. But there it is.
Thank you for teaching
I
us
really
this.
didn't know that
You don't have
part.
to struggle either.
Yeah, this is pretty sweet. Anybody have any questions? Yeah. So we have a bunch of these calculators, if you don't want to buy your own. We have a bunch of them in the classroom, and you are welcome to use them all class period every time. We just need to put them all back, because we're starting out with them full, and we need to end with it full. This last year, they just slowly disappeared, because I wasn't very careful. Yeah, so they bought some new ones, but I'm not allowed to do that again. I was told to trade the calculator for like an ID or something. I don't think that's worth doing for a calculator, right? If you need to borrow the computers, I'll take something of value in exchange. Cell phone, car keys, ID, something like that, okay? Just to make sure it comes back. Oh, we didn't finish. We got all excited because we found the order. Well, great. We found this. So what I'm going to do now is I'm going to copy that. And paste it in there. So we have some more room. So there's the rate law. What's the rate constant? Yeah, you had a question?
Yeah, can you explain again what you got that one from? Did you put double the first,
Because when we double this, oops, wrong place. When we double this guy and keep this one the same, that one doubles. And you could also, you can only do that for those two though, because here we have this guy changing also. So you have to pick them carefully when you have multiple reactants.
so why didn't we use the third and the fifth?
We used the third and the second and the third one because we wanted to find the order for this. So we wanted this to change and we wanted that to stay the same. Yeah. Because then the things cancel out. It just makes everything simpler. You could do, this one and this one, or, some other combination. But then you're going to have to put those numbers in and do math, and it's, yeah. So the rate constant. As I mentioned, real data, there's error in the measurements, right? So if we solve each of these lines for the rate constant, we're not going to get exactly the same number. And that's expected. So what a scientist does is they're going to do it multiple times, take the numbers and average them. Because most of the troublesome error is random, meaning sometimes it's too high, sometimes it's too low. You take a bunch of measurements and the error cancels itself out. We trick it into going away. So let's just do this last one because those numbers are feeling lonely because they haven't gotten used yet. They're like, why are we even here? You don't need to be there. We could do this whole thing without you. So we're going to take our rate constant, or rate law here, and we're going to plug the numbers in. So the rate is 0.027 molarity per second. That's equal to the rate constant, which is what we don't know, times CHCl3 concentration, 0.040 to the first power, times the Cl2 concentration, 0.040 to the 1/2 power. So people who are good friends with math can solve that. No problem. What if you're not good friends with math? Let me show you how to use the calculator again. Did I do that right? computer fell asleep. I'm glad that most of you are awake.
That's funny.
Thank you.
I'm here in body and spirit, just not mind.
Okay, well, we'll take what we can get.
Exactly.
So I'm gonna go into the number solver, and the equation I had there before comes up again, which is great if you're doing like similar things, or if you got it wrong, you can go back and see it and you're like, oh shoot, I just got the wrong number there. You can just fix it, you don't have to type it all over again. But this is completely different, so I'm gonna clear and clear. So on the left, I have 0.027. On the right, I have K. We're gonna call K X today. X times 0.04. The 0 at the end is a significant figure, but the calculator doesn't care. One of the drawbacks to using this is there's a limited number of characters that it will let you put in. So sometimes you'll be typing along and you're like, it's not taking any more characters. Then you need to go back and do things like get rid of the 0 before the decimal point, get rid of unnecessary parentheses, stuff like that. So 0.04 to the first power times 0.042, I could put 1/2 here. Let's do that. Or I could put 0.5. You see how the 1/2 is all up there in the superscript? Yeah, it needs to be all up there. And I press enter. I'm going to start it at 0 again. 3.375. $3.375. Any questions?
Yay! So in the last problem that we did on the calculator,
Mhm.
our x was, because we were looking for the order.
Yeah, so the last one that we did this way, we were looking for n, and we called it x. Here, we're looking for k, we're calling it x. Because for $25, you don't get the whole alphabet, right? They're just going to give you some of the letters. Any other questions? Yeah.
What units are, or what units will?
Yeah, that's an excellent
K
question.
be?
Thank you for asking, because that's what I was getting to next. And I realized that I forgot to put all the units in here, so I will fix that. Okay, so let's look at the units. An excellent question. So we have molarity per second on this side. We have our rate constant. Then we have molarity to the first power and molarity to the 1/2 power. Well, I could factor an m out of both sides, right? This numerator doesn't disappear. It's a 1, okay? And now we have that 1/2. Let's divide by m to the 1/2 on both sides. And this has units of 1 over m to the 1/2 seconds. Aren't those pretty? Yeah, very nice. Rate constants often have just like weird units. Is that unit meaningful? No, it's not. Why is it there? It's there because we know the concentrations were moles per liter, we know the rate was molarity per second, and we need them to work themselves out. So that's what is needed to work it out. It's whatever it needs to be. Any questions? So here we have another reaction with no. This reaction is first order to O and second order to no. Is it second order because of this coefficient of 2? No.
No.
No, it's not.
No.
Coincidence. Maybe an unfortunate coincidence, but there it is. So they want us to look at these three pictures here. Oxygen is the two red circles. No is the blue and red circles. And pick out which of these would have the fastest initial rate. So let's just sketch, or not. No, that's not what I want to do. There. You thought I was lost, but I'm not lost. Just confused. Rate equals rate constant times O2 to the first power times no to the second power. Which concentration affects the rate more?
No.
No.
Oh!
Yeah. No, I like that you're getting into it. Thank you. So let's look at these and figure out which one has relatively more. No. Here we've got half and half, right? 3 of each. Here we've got 2, no, and 4 oxygens. Here we have 4, no, and 2 oxygens.
What's the actual name for
That's an excellent question. Nitrogen monoxide.
that? Monoxide, okay.
Yeah,
Oh.
yeah. I think no
Oh, yeah.
is more fun.
Oh, wait.
Nitrogen monoxide. And then this is nitrogen dioxide. Yep. So this one has 4 nitrogen monoxides to oxygen. So this 4 is going to get squared, right, to 16. And we put the 2 in there. 2 times 16, 32. Here, we've got 2 nitrogen monoxides. 2 squared is 4, times 4 of those is 8. If we did this one, we have 3 of these. 3 squared is 9, times 3 is 27. This guy wins. Does that make sense conceptually? Because this is second order, it affects the rate a lot more. They both affect the rate, but the no does it more.
Can you say that again? Sorry.
I will try. They both affect the rate. Both concentrations affect the rate, but no affects it more than oxygen because this concentration is squared and this one is not. If they were both 2 or both 1, then this one would be the fastest. But because we have more, no,
No.
here, and that's squared, this one's going to be the fastest. Yeah.
So for E, would it be O2 would have to be squared?
If O2 was squared and no was first order, this one would be the fastest. Yep.